And the principal part of the curve will yield the principal value of the arc sine. And there is only one such value for the arc sine. The principal value for arc sine is the measure of the angle between minus 90 degrees and plus 90 degrees. And that is on the graph from here to here. Let me trace the curve in red. That's the principal curve. We usually denote the restriction on the inverse function of a given trig function by using a capital letter for the arc sine. So more technically, the capital A arc sine theta ranges between minus 90 degrees and plus 90 degrees. Yet the arc sine with a small a is the entire inverse curve. Similar comments can be made regarding the cosine curve. The graph of the cosine curve will be drawn, and it goes something like this. Starts here, comes down to minus 1, comes back up here to plus 1. Of course, it continues on, but we just want to look at one cycle of the curve. Now, once again, if we draw a line at 45 degrees through the origin and treat it as a mirror, we will be able to determine the reflection of it in this mirror and hence obtain the inverse curve. The inverse curve begins like this and goes through like this, on and on this way, and of course on and on this other way. So what you have is the same kind of sinusoidal curve going along the y-axis as you do along the x-axis. Once again, for any given functional value of x, you will have an infinite number of solutions. If I take, for example, an easy angle such as the cos of 60 degrees, which also happens to be equal to 1/2. Cos of 60 is approximately here. You can see a vertical line drawn in the graph will cut the curve in an infinite number of places. On my graph I have a cut there, I have a cut here. You can anticipate a cut over there, another over here, and as the curve goes up or sideways this way, it'll cut that value 1/2 an infinite number of times. And so once again, we want to deal only with the so-called principal curve of this inverse cosine function. And the principal curve selected is the part from 0 to 180 degrees. And so from 0 to 180 degrees is the amount from here to here. And let me now outline it. Therefore, if you follow the inverse curve from 0 to 180 degrees, it begins here. I will outline it and stops right there. And of course, the principal curve yields those principal values within the restriction from 0 degrees to 180 degrees. Consequently, 0 degrees is less than or equal to capital A is less than or equal to 180 degrees. And so the measure of the inverse cosine function will be restricted between those limits. That is how most calculators are are constructed so that the principal values are the values that are displayed. And finally, for the inverse tangent, we can construct the tangent function, draw the 45-degree line. The curve itself, y equals tan x, is drawn something like this, where the asymptotes occur through 90 to 70, etc., 180 degrees apart, and the curves become, I'll draw the one here in the center, it's the only one we really need, comes in here like that, and then comes down like this. This is minus 90. The curve through the mirror here will be of this shape. It'll be asymptotic here at minus 90 and at positive 90. It's pretty obvious this time that the limits of the principal curve, which I am now drawing in color, is between minus 90 degrees and plus 90 degrees. For example, determine x in sine x equals 0.6500 in degrees, minutes, and seconds. If we take the calculator and place in the display 0.6500, and then the inverse sine of that is taken, then the arc sine of 0.6500 is equal to 40.54160187 using the full display. That is the principal value of that quantity between minus 90 and 90 degrees. We therefore have that the angle x is equal to 40 degrees. Taking a fractional part of a minute, the result is 32/30 seconds. You can see from this problem that the answer for the angle x can amount to an infinite number of solutions. On a quickly constructed graph, if we treat this amount as the angle which gives the sine of it equal to 0.6500, we find that there is another such angle that produces the same amount of 0.6500, and it is the related angle 180 minus 40 degrees, 32 minutes, and 30 seconds, which in this case then is equal to, by subtracting 139 degrees, 27 minutes, and 30 seconds. The infinite solution here then is 40 degrees, 32 minutes, 30 seconds, plus I times 360 degrees, where I is an integer. Similarly then, for 139 degrees, 27 minutes and 30 seconds, 139 degrees, 27 seconds, 7 minutes I meant to say, and 30 seconds plus I times 360 illustrates the infinite solution for the trig function whose value is equal to 0.6500. We could say then that this is the answer for small a arc sine 0.6500. But for capital A arc sine 0.6500, there is only one answer, and it is 40 degrees, 32 minutes, and 30 seconds, or 40.5416087 degrees. Another example, calculate the angle between minus 360 and positive 360 degrees in which the sine of x is equal to negative 0.9. The arc sine of negative 0.9 using the calculator is equal to negative 64.1580672 degrees. The other angle, whose sine is equal to negative 0.9, must be in the third quadrant there. And it is equal to 180 degrees plus 64.1580672. So we have these two angles so far which satisfy the given functional value of negative 0.9. Negative 64.1580672 degrees, and this sum, which equals 244.1580672 degrees. But you'll notice that we have other solutions too that are related to those angles. In other words, if we continue with this rotation angle, you can see that that is equal to 360 degrees minus 64.1580672. So x also equals 360 degrees minus 64.1580672 degrees. That'll amount to 82391485 and 2. So here we have another solution between negative 360 and positive 360. That's the third solution we've found so far, and yet there is one more. And in this last result, which is this rotation angle, you can see that it is equal to x equals, take it, negative 180 degrees plus 64.1580672 degrees, and this results to the answer 8239148511 degrees. So it's negative 115.8419328 degrees for the value x. And all of these results range between the limits negative 360 degrees and positive 360 degrees. If you placed any one of those quantities in your calculator and worked out their sines, their trigonometric sines, you will get negative 0.9 as the answers. In another example, we're given that the secant of x is equal to negative 1.7525, and we're to find the value of x between 0 degrees and 360 degrees. There is no inverse trig function for secant on your calculator, What you'll have to do, therefore, is deal with the problem through the inverse trig function cosine, which is the reciprocal of secant. So we turn the question around and look at the solution this way. The cos of x is equal to 1 over the sec of x. And so that in turn will be 1 over negative 1.7525. If we take the reciprocal of that amount, then the cos of x is equal to negative 0.570613,409. Dealing with the inverse key for cosine on your calculator, we establish the number of degrees as 124. X is equal to the arc cos of negative 0.570613,409, and this in turn is equal to 124.793 approximately degrees. Since the cosine of x is a negative quantity, then there are two quadrants where this angle, the function of cosine, equals this amount. It is, as you can see, in the second quadrant, and the other answer will be in the third quadrant, and we have to work that out on the side. This is the one answer, 124.793 degrees. The other answer will be 180 degrees plus the angle. So the other solution for x is equal to 180 degrees plus 124.793 degrees, which amounts to 304.793 degrees. Consequently, for the sec of x to equal negative 1.7525, then x is equal to 124.793 degrees and 304.793 degrees. Next, we will solve for a variable in a trig equation. For example, solve for x in y equals cos brackets x plus pi divided by 4. The quantity x is connected with pi over 4 through the plus sign. And so the pi over 4 somehow has to be eliminated from that side of the expression. Of course, the whole amount, which is in brackets, is tied up by the cos function. It's the cos of this quantity. So this cos function must be disconnected, so to speak, from that expression in brackets. And the way to do that simply is to take the arc cos of both sides, leaving x plus pi by 4. Now you simply subtract pi by 4 from both sides, and x is equal to arc cos y minus pi over 4. Be careful with this. We don't want you to think that y minus pi over 4 should be placed in brackets. That would change the solution. Actually, it might be better and clearer if we wrote pi by 4 first, plus arc cos y. In another example, y equals 10 times the cos of 6x minus 3 pi. Solving for x again, see that 6 has to be removed somehow. The 3 pi must be removed as well. There should be no cos or 10. X must stand as a single variable by itself on one side of the equal sign. So all those parts have to be disconnected. We first start with the 10, which is multiplied by cosine, and so by dividing by 10, y over 10 is our result. We cannot work with the parts within brackets because it is controlled by the cos function, so to speak. So we have then that y over 10 is equal to cos of 6x minus 3 pi. To remove the effect of cos on that expression in brackets, take the arc cos, and we write arc cos of y over 10, and we're left with 6x minus 3 pi. Do additions and subtractions first when you get to this stage, and so we add 3 pi to both sides. We end up with 3 pi plus arc cos y over 10 is equal to 6x. Finally, divide by 6, x by itself there. This amount becomes 1/6 of arc cos y over 10. Don't put y over 60 there. That would be wrong. And dividing by 6 here leaves pi over 2. In one more example, I have 4y equals 2 arc sine 5x plus 7. Solving for x here, we have to eliminate all those parts that are connected with x in one way or another, so that we end up with an equation with a single variable x on one side. We will subtract 7 first and write 4y minus 7 equals 2 arc sine of 5x. The 2 will be removed by dividing 2 on both sides. 4y minus 7 over 2 is equal to the arc sine of 5x. Disconnect the effect that arc sine has on 5x by taking the sine of both sides. Taking the sine of both sides will disconnect that, and we can write the sine of 4y minus 7 over 2 is equal to 5x, and finally divide by 5 to get x by itself. Careful where you divide by the 5. It's 1/5 of this left side, and so it's 1/5 of sine 4y minus 7 over 2 that x equals. The next topic is plane trigonometry, or the trigonometry of the plane. We'll review the definitions for sine, cosine, and tangent of a right-angled triangle. Just briefly, sine of an angle x in a right-angled triangle is the opposite over the hypotenuse. The cosine of an angle is the adjacent over the hypotenuse, and the tangent of an angle is equal to the opposite over the adjacent. Two angles whose sum equals 90 degrees are called complementary angles. Two angles whose sum is 180 degrees are called supplementary. For two complementary angles in a right-angled triangle, the sine of x is equal to the cosine of 90 degrees minus x. And this works in both directions. In other words, the cos of x is equal to the sine of 90 degrees minus x. Similarly, the sec of x is equal to the cosec of 90 degrees minus x, or in other words, the cosec of x is equal to the sec of 90 degrees minus x. And finally, the tangent of x is equal to the cotangent of 90 degrees minus x. The cotangent of x is equal to the tangent of 90 degrees minus x again. Here's an example from the top of a cliff that's 75 meters high. The angle of depression to a boat is 32 degrees. How far is the boat from the base of the cliff? First of all, I'm going to explain what the angle of depression is. If we take a horizontal line and assume you are the viewer towards the horizon from that point, then if you look down from the horizontal, that's referred to as the angle of depression. If from the same point, using the horizon as a reference, if you look up in this direction, that's called the angle of elevation. In this problem, we're going to construct a diagram representing information we have, and we'll assume this is the cliff and we have the water there, and the angle of depression is taken from that point. We're not going to consider the height of the person or the transit that's used in the measurement of the angle and so on. Just take it simply as being represented by this diagram. And so the angle of depression is the line of sight to an object, in this case is the boat. It is known from the problem that this is 75 meters high, and the angle of depression is 32 degrees. We'll assume we have a right-angled triangle here, and what is required is the distance from the boat, which is located at that point, to the base of the cliff. Let's call this some letter like x. We have two sides. We have one side given in the problem and an angle. And in this right-angled triangle, then, what we'll have to do is use the information required, use the information given by the angle of depression, and noting that if this is a 90-degree angle, which it is, then this angle in here must be equal to 58 degrees. 58 plus 32 is 90 degrees. It follows from a trig function that involves x and the side given that x over 75 is a tangent ratio to the angle 58. So x over 75 meters is equal to the tan of 58 degrees. And so x can be found by taking 75 and multiplying it by the tan of 58 degrees. At this point, and we have 120.03 meters.